It is a great pleasure for me to introduce our next speaker, Professor Daniel Cremers. Daniel Cremers is professor at the Technical University of Munich in Germany. So he's very well known for his outstanding contributions to computer vision, and he received a number of well-deserved awards and grants, including most recently an ESC Advanced Grant. So one of his many well-known contributions to science is the direct approach for visual SLAM. So which led to the well-known methods like LSD SLAM, DSO SLAM, or DV3O. So, and recently, he is also applying his expertise to the domain of autonomous driving through his company, Artisense. So very related to this, today he is talking about latest research in the area of visual SLAM. So Daniel, we are very glad to have you here and we are looking forward to your talk.
Thank you so much for having me. It's a great pleasure to be here. Thank you for the nice introduction. I think this workshop is really great, and I'm happy to be able to share a bit of our research in this great workshop. This is, as the title indicates, is on how to use deep learning, in particular self-supervised learning techniques, to boost visual SLAM, and in particular visual localization, visual odometry. I should say upfront, the work that I'm presenting has been done predominantly by a number of current and former students of mine, in particular Nan Yang, Lukas von Stumberg, Roy Wang, Felix Wimbauer, and Jacob Engel. Maybe a bit of background on how I got into visual SLAM. We started around 2007 with autonomous, with building drones. The first ones we assembled ourselves. On the left, this is a picture from 2007. In fact, a little drone flying in my office, and I was very amazed at them. At the time, they were not commercially available. In the subsequent years, they became commercially available, and so we started buying more commercial versions of all of these drones. And then we, either they had cameras or we put cameras. For example, the nanocopter on the right did not have a camera, so we had to equip it with a camera. And then we asked ourselves, can we use onboard sensors, in particular cameras, to do autonomous navigation? And so this requires somehow camera-based localization in real time, and you want precision, you want robustness, etc. And so in the subsequent years, we managed to get some systems to work. First on existing, like top left is Jacob Engel's work using the PTAM, a very nice real-time capable visual SLAM system that creates maps. And so you can use these maps to do autonomous navigation, either figure flying or just making it hover in one space. And then we moved on with nanocopters, autonomous nanocopters, visual exploration, path planning, obstacle avoidance, free space estimation, all of this using predominantly onboard cameras. But what it really implied is that we started moving more and more into developing SLAM methods, because we found the SLAM methods out there were good, but often not sufficiently robust, not sufficiently scalable to larger environments, or not sufficiently precise. And so we looked into this. And so in the first part of my talk, I want to give a little glimpse into research on, say, classical SLAM approaches, and what Fritz mentioned, that the direct SLAM approaches that we've been advocating, LSD SLAM and direct sparse odometry in particular. And in the second part of my talk, I want to give a glimpse into how we can use the predictive power of deep networks to further boost the precision and to kind of get them a much more powerful SLAM and mapping framework. I should say there's a lot of different facets of SLAM, of camera-based reconstruction. Here we really focus on this scenario of real-time capable methods that try to recover the world from ideally a single moving camera. So not the classical kind of bundle adjustment where you can, often compute hours to get often much more precise reconstructions, but typically not real-time. The whole field is a very kind of old field, and this is one very classical work that many people know. It's a work by Erwin Kruppe, Austrian mathematician, who proved in 1913 that if you observe 5 corresponding point pairs in 2 images, then you can recover the relative camera motion, translation, rotation of the camera, and the 3D location of these points. And for me, this is always a bit puzzling how people more than 100 years ago, well before the advent of computers, worked on such problems. But this is obviously, they did this in this field of photogrammetry, where often you manually labeled corresponding points in photographs, aerial photographs, and then you wanted to recover the location of these points and the relative motion that the airplane made. And so this does make sense in this setting, but one should say this was pioneering work that the vision community in the 70s, 80s, 90s built up to develop really powerful, and starting around 2000, real-time capable methods for what was originally called structure from motion or structure and motion, and is now increasingly called visual simultaneous localization and mapping, visual SLAM. And indeed, this is just a few kind of representative and I would say quite pioneering works that paved the way. There's a lot of more publications, obviously, in that field that I was not able to mention here in this short period of time. But I think this is a number of works all the way to one of the most popular methods these days, a technique called orb SLAM, very powerful technique from a team in Zaragoza. And orb SLAM, much like many of the others, actually does follow in many ways in the footsteps of Kruppe, in the sense that they take images, they extract points, they compute correspondences between points using certain descriptors, in this case orb descriptors, for example. And once they have corresponding point pairs, then they can run a lot of the machinery that was pioneered by Kruppe and others, ultimately some form of bundle adjustment ideally. But nevertheless, I think there is always reason or time to question the pioneers and to check, is that really how we should do it? So this is what we call the key point based approach. And it does this intermediate abstraction step of extracting points, computing correspondence. And as you all know, for anyone working in this field, computing correspondence is actually one of the nastiest problems in computer vision. And the question is, if you make any mistakes in correspondence estimation, they are invariably going to propagate into your reconstruction. And typically, these key point-based methods have trouble recovering from incorrect correspondences. Obviously, you can introduce heuristics like ransack and resample correspondence, but this is a tedious kind of endeavor. It can be made to work, and it's actually quite powerful, but nevertheless, I think one alternative is to revert to what we call direct methods, techniques that directly kind of tap into the sensory data, the raw brightness values of your camera to recover 3D structure and camera motion. People often say, what's the real difference? The real difference is that when you look at the reconstruction, the classical methods, what they minimize is a geometric reprojection error. That's what bundle adjustment does, right? Whereas what we minimize in these direct methods is a photometric color or brightness consistency error. The idea being find a reconstruction of the world and a motion of the camera such that the colors across the different images coincide. And so it is the brightness consistency, much like in what inspired us in optical flow estimation, that's what drives all the estimation. And this is one work in this line of work. It's a technique that we called LSD SLAM for large scale, direct SLAM to my knowledge. Among real-time capable visual SLAM methods, I think it was the first large scale capable one. I'll show you in a second what we mean by large scale. This is a fairly sophisticated approach, but it has different modules that go in alternation. So in particular, there is a camera tracking and a depth estimation that are being alternated here. And if we, let's just look into the tracking component. So the image stream comes in, say at 30 Hertz, and then there is a component that tracks the camera, and essentially the loss function we minimize here is this brightness consistency. You have a keyframe image, you have the current image, you have a keyframe depth, and now you find a rigid body motion GXI with 6 parameters modeling translation and rotation, such that the brightness functions are aligned for all pixels X in the image plane omega. So really all brightness pixels in principle can contribute to this estimate. The reason why this can be computed very fast and in real time, even on a single core of a CPU, is we're only estimating 6 parameters here, right? So we can easily do a course to find linearization of this and run this in real time on a single core of a laptop. And then you can, on the remaining cores, do depth estimation in alternation, and this leads to this method LSD SLAM that you see here in a demo system. It's running on the laptop CPU in real time. It's tracking the camera, and it's estimating, as you can see in real time, the point cloud and the location of the camera. Here we accelerate things a little bit, but you can see we can really, with just one single camera, map fairly large environments, meaning not just a desktop environment, but really a whole outdoor scene with pretty much no drift, or very little drift, at least, as you see. In LSD SLAM, there was a component that was deliberately inserted to remove the drift. This was a loop close ring technique that we adopted from LiDAR-based SLAM. And that kind of closed loops and thereby reduced the drift. And since the work of LSD SLAM, our main effort has been fighting drift. How can we further and further decrease drift to make the precision go up of this visual odometry approaches? The follow-up work to LSD SLAM was a technique called direct sparse odometry. This is, you could say, the next generation. Here's a video, top left input video. You see there's even people walking through the scene. The assumption is that the world is static, but essentially moving objects are filtered out or ignored by the robust loss function. And as you can see, in real time, we can track the moving camera and map the outdoor environment at fairly high precision. The difference to LSD SLAM is that we do a windowed optimization over the last 7 keyframes that are being jointly optimized, or last n keyframes, however many you can do in real time, right? And essentially, the other key difference is that camera motion and 3D structure are jointly optimized, not by alternating 2 different threads, but really in one Gauss-Newton optimization. And the only way to get this to real time was actually to do a windowed optimization. And this was kind of the key to making it real time capable. And you see, obviously, if you track the camera motion over thousands of frames here, you will create errors that will accumulate into what's often called a drift. And as a result here, the bicycle that you see in the top left image is actually reconstructed twice, right? And there is an offset of what, maybe 2 or 3 meters on a distance of hundreds of meters. So you could say the drift is somewhere in the range of 1%, maybe, with respect to the total travel distance. But the question is, how do we quantify the drift in the real world, right? Obviously, we can take it to a simulated world, but what we observed is that a lot of powerful SLAM techniques that were demonstrated to work really well in simulated environments, they often fail miserably once you carry them to the real world, because the world we live in is just not a simulation, at least not to my knowledge. And so you want to capture the real world. And so this is what Jacob Engel did here. He took the camera, actually different cameras with different lenses, quite a variety of more perspective, more fisheye lenses, some indoor, some outdoor, some faster motion, some more rotational motion, lots of different sequences. They all have one thing in common. They all loop back to where they started from. And as a result, we can quantify. We don't know where the camera was halfway through each sequence, but we know where it should be at the very end of each sequence. And so we can compute a total drift in terms of translation, rotation, and scale drift. And what we plot here is on the x-axis is the total drift, and on the y-axis the number of sequences where we achieve that total error. And obviously, you want to have as small an error as possible for as many sequences as possible. So you want to be in the top left corner of these plots here, right? And this is a comparison to what we consider the state-of-the-art orb slam. The dashed line is real time. The solid line is if you have a bit more compute time. This is all measurements from 2016 or 17. So by now, these curves will have shifted in terms of what's real-time capable. But what you can observe, you can read this in many ways. For example, you can say, what's the total, what's the error on the best 300 sequences, translational drift on the best 300 sequences, whereas orb slam achieves an error of 6. DSO achieves an error of 1. So it's a dramatic reduction in error. Or you can say, what is the, if you want to impose a maximum error of 2, how many out of the 500 sequences can you track with that error? Orb slam can track 100 and we can track 400 out of 500. So also you could say a dramatic boost in robustness, because obviously you want these methods to work not in 1 or 2 sequences, but in as many different sequences as possible. There's more evaluations also with respect to, moving backwards and forwards, also with respect to downsampling the images, something you might want to do to accelerate the performance. We found these direct methods are much less sensitive to downsampling because they don't use key points. And so the key point extraction or detection doesn't depend on the specific resolution of the image. They are much more, so the direct methods are much more sensitive though to geometric distortion. So for example, if you have rolling shutter cameras, typically direct methods do not perform that well. So there are some strengths and weaknesses here, I should say. But that inspired us, these works inspired us to create a startup company, Artisens, which has the aim to kind of commercialize and bring these localization and mapping techniques to the market of autonomous systems. Self-driving cars, driver assistance, autonomous robots, flying drones, you name it, right? Artisens has big cars, but they also have toy cars where we can test these algorithms. One of the first algorithms developed at Artisens was stereo direct sparse odometry. So this is an extension of DSO to 2 cameras, and that gives you 2 benefits. First of all, you can actually estimate the scale of the world, absolute scale, because you have a baseline. And secondly, you further decrease the drift to a level where you can really drive around the block, as you see here, and have almost no drift, right? This particular system is not using loop closuring. Obviously, you can add loop closuring to direct sparse odometry as well to eliminate loops. But here you see the drift. This you can apply. There's lots of videos, so I'm going to just skip over this. If you want to watch the videos, you can go on YouTube and see more of these. Artisens develops the sensory systems because one of the things we found is if you want to fuse this from multiple cameras and if you want to merge it with IMU information, with GPS, RTK, GPS, and other sensory information, then you have to start developing these sensory systems. Often there is no off-the-shelf commercial systems that have sufficient precision in synchronizing, in time stamping, etc. So this is one thing that Artisens has been developing. And secondly, they develop spatial AI algorithms. For example, Artisens had a project where they deployed their sensors on a whole fleet of cars in Berlin. And they drove 8,000 kilometers of distance and mapped large parts of Berlin in just a few days. And as you can see here, these are semantic maps, so we can distinguish drivable area, sidewalks, vegetation, buildings, other cars, you name it. Right? Whatever you can detect in images with deep networks, obviously you can label the 3D world and get semantic 3D point clouds. And I think this is vital information for autonomous driving, right? Because you want to see where are obstacles, but you also want to know what obstacles am I looking at, right? And I think to date, the vision community has been very much focused on labeling images, but I think for autonomous systems, we really need to move into modeling the 3D world and labeling not the images, but the 3D world. And so all of this can obviously be done. Here you saw already a glimpse of where deep learning comes into the play for extracting semantics. But a second question is obviously, once you're interested in localization and mapping, can we use deep networks to boost performance here? And deep networks have been around for a long time by now, but in the field of 3D reconstruction and SLAM, it seems to be much more difficult to make advances. For object detection, recognition, categorization, they worked really well, but somehow reconstructing the 3D world with deep nets is, I think, to date, an important challenge to focus on. And there has been a lot of work, starting a bit later, though, starting around 2017, people proposed all sorts of deep network techniques. This, again, just some representative work. Deep networks to do visual SLAM, localization, mapping. And although these methods are quite impressive in many ways, that you can train a network end to end to recover these structures, often they did not exhibit state-of-the-art performance on the established, say, visual odometry benchmarks, where the classical energy minimization techniques still outperformed for a long time. And I think, it's hard to reason why this might have been the case, but I think this end-to-end learning, say in goes the video, out comes the 3D world, maybe we're not there yet. Maybe we need to devise what I call hybrid techniques. And one of the areas where deep networks can really help is, it turns out you can train networks to predict depths from just one single image. This is a really nice work by Kuznetsov and collaborators, 2017. We built up on this network and further improved it, a network architecture that we call StackNet in 2018. And as you can see, it gives depth predictions even more precise than the Kuznetsov work. It's not surprising that this is possible in some sense, because if I showed you this image as a human and asked you, can you tell me how far things are? Obviously, humans are not good with exact numbers, right? But, roughly you could say so. And if humans can do it, machines should be able to learn it from training data. And so this is what the StackNet does. But next, what we can do beyond just predicting depths, we can fuse that depth prediction into a classical SLAM pipeline. And we can do so both on the front end and the back end. The front end tracking of the camera in terms of a nonlinear factor graph where we can add these as constraints, but also in the back end SLAM pipeline where we can add a term in the loss function saying the reconstruction that you're generating here should be maximally consistent with the depth prediction for all the keyframes in my video. And once you do that, you get this is called deep virtual stereo odometry. We called it deep virtual because it uses the second camera in the training phase. So in the application that you see here, we're only tapping into one single camera, meaning no stereo, no visual, no inertial, no GPS, nothing. What you see is mapping in real time from just one moving camera. And you can see there's, compared to the baseline monocular approach, the deep learning enhanced monocular one has pretty much no drift or very little drift. And this is because it uses the depth predictions, in particular, no scale drift. Why? Because the depth is predicted in metric units, right? In meters. So the network knows the scale. And I was a little bit proven wrong, right? For years, I told my students in all my classes that you cannot estimate the scale of the world from a single moving camera. We all learned that in geometry, right? And structure for motion, right? But turns out I was wrong, right? If you know the world you drive through and you train a deep network, then you can predict metric distance and scaled reconstructions. Here's comparisons, and in fact, you see it's actually it outperforms a lot of the state-of-the-art stereo methods, although it's only a monocular method, really. The title is misleading. In a lot of literature, people call this a stereo method. It's virtual stereo because the second camera is hallucinated by the deep network, essentially, right? So we can compensate for the missing second camera by a deep network. And this is what we consistently see. I'll come to that in a second, that the deep networks allow to compensate for missing sensory information. because we can go further. We can not only predict depths, we can also predict, once we have two consecutive images, let's call them IT and IT prime, we can predict the relative pose, and we can predict some notion of uncertainty and feed all these deep network predictions into the SLAM pipeline again. So more specifically, from one image, you can predict depths. From two consecutive images, you can predict the relative camera motion. Let's call it T, large T. And then you can train the network like we did before in a self-supervised manner. This is very important, right? Deep networks, I think, still to date are often based on training data, ground truth that you need. And for 3D reconstruction, you typically don't have ground truth. And if you take LiDAR depths as ground truth, we tried it. It's not a good idea because the LiDAR measurements are quantized. Well, guess what? The deep network reproduces the LiDAR quantization, right, in your ground truth. You don't want that, right? So you want something that scales better, that doesn't need ground truth. And here, what do? We take the brightness consistency as a residual. We can warp the two images based on the relative motion and then say the brightness consistency is the loss. Once you do that, though, for real cameras, you have aperture changes, and so the brightness is practically never preserved. There's typically, all sorts of brightness variations. But here, what can we do? We can model these with an affine brightness correction, and we can train a deep network to predict the affine brightness correction. And that way, we can not only warp the images based on the relative camera motion predicted by the deep net, but also we can align the brightnesses affinely based on the deep net prediction of the affine correction. And then we can do self-supervised learning, and this is going to work for Lambertian worlds, right? Because these are, the brightness is by definition preserved. Unfortunately, once you take this outdoor, the brightness of things is not always preserved. In windows, you don't have brightness preservation. In metallic structures on the cars, maybe even in the moving trees, you will not have brightness preservation. So what can we do? We can train a network to predict, and this is work by Kendall and Claude et al., who proposed networks that predict what's often called an aleatoric uncertainty. And then we can basically saying which areas in the image are likely not to have brightness preserved. And this is the bright areas on the bottom right here. And then we simply downweight all the residuals by this uncertainty, right, to correct for this effect and to filter out those areas in the image where brightness is likely not preserved. The network learns all of these parameters. They are all fused into the SLAM pipeline, and out we get a method that is very powerful. We compared here both to, in terms of the depth prediction, to what was the state-of-the-art monodepth 2. And you can see we are significantly better than monodepth 2 in terms of the depth prediction of this network, both on Kitty and on Europe. Also, the aleatoric uncertainty here actually can be predicted and even generalizes to other data sets. We trained on Kitty, we apply to cityscapes, and as you can see, both the depth prediction and the uncertainty prediction are fairly meaningful. But coming to the next, we want to see how accurate is the visual odometry. And here we compare both to mono and stereo methods, state-of-the-art mono and stereo methods. And you see the method is significantly better than these, but also to hybrid methods, deep learning-based methods, either end-to-end trained or hybrid methods. And you can see a significant improvement in visual odometry. In fact, we can compare to state-of-the-art stereo inertial methods, methods that use two cameras and an inertial sensor, in this case, basalt. And you can see the proposed monocular approach is on par with the best stereo inertial method, even though it only uses one single camera and no IMU. Right? So in some sense, again, it confirms that the deep network predictions help to compensate for missing sensory information. They boost the precision and robustness of these methods to a level that they can rival with very, much more sensory heavy techniques. Here's a comparison, mono DSO reconstruction, D3VO reconstruction. This is the deep network enhanced one. And you can see the reconstruction is much crisper. This is because the visual odometry is much more accurate. And so there's no drift. And so the point clouds align much better. And lastly, this is work coming up at this week's CVPR. We can actually train deep networks to generate dense maps of the world from a single moving camera. This is what we focused on here. And this deep network is a little bit involved. It has 3 components. First is a cost volume component. So rather than predicting depths from a single image, we take a set of images and create a cost volume. This has been done in other network architectures before. Please refer to the paper for the prior work there for this cost volume predictions. And then there is an additional component, this is the real novelty here, is we combine this cost volume based depth prediction with a motion masking module. It's a module that is trained to detect moving objects, and then these are filtered out in the depth prediction. And so the depth prediction and the whole network, basically, there is a component that compensates for moving objects. So the first part of the network aggregates brightness from multiple warped frames, and then basically you can use the brightness inconsistency across frames to identify the moving objects in this mask module, because the moving objects are exactly those where brightness prediction consistency is violated. And as a result, we get a method that takes a single camera stream. This is this one, I think, of the kitty sequences, if I'm not mistaken. And as you can see, it reconstructs a fairly large environment from just one moving camera. And I think this is useful because it allows you to, in essentially or near real time, create dense reconstructions of the world of this type from just a single moving camera. And I think this is something that is becoming increasingly important because a lot of people who work on self-driving cars, they need environments to train self-driving cars to test them, right? And you don't want to do too much testing in the real world for all the damage and accidents you can create, right? And so here we have a way to virtualize the real world with just one moving camera. So I recommend, if you're interested in this work, it's a technique that the first author, Felix Winbauer, called monorec for monocular dense reconstruction. And feel free to visit his presentation later this week. That's it. Thank you very much for your attention. So here's a short summary: LSD SLAM, direct sparse odometry, stereo DSO. Using deep networks to boost performance, using deep networks to extract semantics, and using deep networks to create dense worlds from a single moving camera. Thank you.
Daniel, thank you very much for this very nice presentation. We now have time for questions, and please write the questions into the chat and I can read them. So I can see that I already have questions here. And I would like to read the first one. So could you explain once more why self-supervised learning method would be better than LiDAR ground truth?
As I
think this refers to the problem with the discretization of the LiDAR ground truth.
So there's multiple issues. First of all, to get ground truth from LiDAR, you have to first drive the LiDAR around. LiDARs are very expensive typically, right? And obviously, if you have the money, you can, you can generate, but you cannot continue generating more ground truth unless you keep a LiDAR in the loop, right? And this is the thing, if you want to create self-driving cars, for example, and you want to mass produce them, and then the LiDAR technology on the roof is $500,000 or in that range, right? LiDARs are often thousands of dollars. Then I wonder how you ever want to commercialize this. Who's actually going to buy that car, right? But beyond that, LiDAR has issues. LiDAR is very sensitive to rain, for example, right, and to fog as well. And then LiDAR has quantization issues. And this is one of the things we observed when we used the LiDAR ground truth, and we trained our network using that ground truth. The network reproduced the quantization errors of the LiDAR. And I think on the long run, this is a trend in all of computer vision, in the whole deep learning field. You want to move to self-supervised or unsupervised methods. And this is what we advocate here, that you tap into this brightness consistency to train the networks. And as you see in our results, it works very well. We don't need the LiDAR ground truth, or any ground truth of the depths for that matter.
Okay, thank you. I think we can move on to the next question. We get a couple of questions here. So the next question is from Guyulu. So how much difference is in the scale recovery between the mono and the real stereo?
If you don't use deep networks, mono DSO has dramatic scale drifts. If I go back to one of the comparison slides, sorry, I have to go back a little bit here. Here. Sorry, now I went back too far. Here's a quantitative comparison. Here you see, for example, on the left, you see mono DSO. You see the reconstruction is really beautiful, right? Except the scale constantly drifts, right? The right thing is too big, the left thing is far too small. You see the system reconstructed this large environment, but the scale constantly drifted. Stereo does not have drift because of the baseline, and the deep network also compensates for drift to the extent that the DVSO is superior to stereo DSO. So you can say the deep network enhanced monocular method in our evaluations actually outperforms the stereo-based method. I'm not saying you should drop stereo, but I'm saying the deep network predictions can boost your performance. And ideally, you might want to use all the sensors you have, but still combine them with the deep network to create predictions that further boost precision and robustness.
Okay, thank you. I have a next question from Hassan. So the question is autonomous self-driving with LiDAR or without? I guess, what's your opinion on this?
That is a very political question, I think, because a lot of the classical car companies, they still rely on LiDAR. I'm not saying that you have to kick out the LiDAR. If you have one in your car, you might as well use it, right? If it's there. But I think, and I'm quite convinced, on the long run, the camera will become the lead sensor for autonomous systems and autonomous cars, even for 3D perception. There's a lot of domains. For example, if you look at the monocular dense reconstruction that I showed in the very end, and you compare that to what point clouds you get from LiDAR, the density of point clouds here is just much higher, right? And anyone who works with it, where is it? Sorry. Right? If you compare the density of points in this reconstruction that we get from just one single moving camera, it's much higher than what you typically get from a LiDAR. And anyone working with LiDAR knows you can increase the point density, but the cost goes up dramatically, right? Here, the cameras they don't cost anything, like just a few dollars, right? Compared to thousands of dollars for a LiDAR, right? And if there's one thing I learned from working with many automotive companies over the last decades, cost plays a huge issue in this field. When we started in 2005 working with Daimler, we wanted to put 2 cameras, right? And the Daimler manager said, no, the second camera is not going in the car because it's too expensive, right? I don't know what that manager is now saying about all these LiDARs, right? Because cameras are really cheap. And you can increase the density of points, you can increase the resolution of cameras with very little cost. For LiDARs, this is different, right? It dramatically increases your cost if you want to increase the point density. So I think there's many reasons why you will move to cameras on the long run. Cost, omnipresence, they're much more lightweight. You can put them everywhere. You know, you can fly nanocopters with a camera on them. You know, try that with a lighter. Good luck, right? The drone is not going to take off because the lighter is just too heavy, right? So there's just so many reasons for using cameras instead of lighters. I don't think you have to drop the lighter immediately, but on the long run, the camera is going to win out, no doubt.
Okay, thank you. We have 3 more questions. I think I would like to ask them to you still. So,
sure.
First one from Yisha. So it looks like the reconstructions do not have any sky, which often appears blue point clouds in SLAM algorithms. So I think this refers to the monorack and that you maybe filtered out the sky.
Yeah, good point. Yeah, I guess we filtered out the sky. That's a good question. I'd have to check in the details of the paper. Obviously, reconstructing the sky is not possible in the sense that there's, you know, everything is color consistent if it's a blue sky. So I think there's some validation in there that allows you to remove the parts that are not reconstructible.
So I think then it's a good opportunity to go to the session when the paper is presented and talk about this in detail, right? And here's another question from Yisha. So how are the details reconstruction measured for these algorithms? I'm not sure precisely what is meant there.
So in this case, our evaluation, all of the things I've talked about, predominantly focus on visual odometry, the precision of localizing your car, your drone, your autonomous systems. And this is what we focused on in quantitative analysis, mostly also because we have ground truth for that, right? And so we can compute accurately what is the error here. But in some sense, as you know, SLAM is a chicken and egg problem. So invariably, the more precise your odometry, the more precise is also your 3D reconstruction. But indeed, one could quantify the reconstruction. We did that for the last works in measuring, in actually quantifying the depth prediction, right? So we have ground truth depths. I guess in this case, it does come from LiDAR, and we could show how accurate we are on that level. So we can also quantify the geometric, the error, the precision in the reconstruction here.
Okay, and I think the 2 last questions that I have here. So scale reconstruction from monocular view by means of DNN suffer from lack of generalization in different domains, as far as I know. When it competes with stereo, could it be due to not very careful selection of validation image sequences?
So this is a good point. As I said, that these methods generalize quite well to other environments. We, for example, trained on Kitty and tested on cityscapes, and it does generalize to other environments. We do observe that, but at the same time, you could, in principle, create a misleading environment. For example, if you reconstructed the world at a Lego scale and then drove through it, then the thing would reconstruct the world, but not in the Lego scale, but at the big scale, because it's learned the size of objects, etc., right? So you could, in that sense, systematically fool the system if you wanted to. Right? But when is that going to ever happen with a self-driving car, that it all of a sudden drives into a Lego world, right? I mean, that's kind of unlikely. So in some sense, at least for certain applications, we can rely on the fact that the world, the system goes through, you know, has certain properties, and these are preserved from one environment to the other. And so this is where we find it does generalize, and the environments where you could fool it are more kind of, you know, theoretical constructs, let's say. right? But nevertheless, you are right, and to avoid the fooling of such a system by creating a fake environment of some sorts, you could tap into multiple sensors to get more robustness. And so this stereo would help. This is why I was saying I'm not advocating to just use one camera. Tap into all the sensors you have, wheel odometry cameras, inertial RTK, GPS, whatever you have, even LiDAR. But what I'm recommending is enhance that with deep networks. And then you should get maximum precision and maximum robustness.
Okay, I would still read the last question that I have here. So maybe you can read this as well as it is. So I repeat this for these other people. So for a depth attack, can we naturally transfer the uncertainty in depth estimation to develop an attack strategy to confuse the deep network and impair the performance? If any, what promising components you may suggest we consider?
Yeah. So as I said, I think this question came before I said the last thing. Yeah, if you create a Lego world of a different scale, then you would fool the deep network. That would be one way to fool it that I could think of. But typically, you know, if you have multiple sensors and a deep network, at some point it gets very hard to fool the system, right? Because the inconsistencies will be detectable. And the next thing is deep networks, as I showed, can also predict notions of uncertainty. And so they might even determine whether something is reliable or not. This is, I think, very important. I didn't talk about it much, but for autonomous driving, you need certifications. You need to also have an estimate of how reliable is your estimate, right? And deep networks can do that for you. They can predict uncertainty. They can predict, how reliable a certain estimate is.
Okay, I think we need to move on to our next presenter. Thank you very much for having you here for this nice presentation and this great discussion.
It was my pleasure. Thank you all. Bye-bye.
Yeah, thank you.
Bye.